In this lecture, we're going to talk about isotopes. Looking right at the word, iso means same. So what is the same in isotopes? We're dealing with the same element. That's so vital. And we should know that the same element is denoted by the same number of protons. So we have, let's in this case, hydrogen. And I have three forms of the same element. I'll write them up here. We have H1, we have H2, sometimes called deuterium, and we have H3, sometimes called tritium. Now, notice in our normal way of writing elements, we put the mass number on top and we put the atomic number or the charge number on the bottom. Now notice in this case, in this example, we're talking about a mass spectrometer, which I'm going to talk about in a second, they didn't give the bottom number. And the reasoning behind that is because they gave me the element. Only the element H holds a certain number of protons. Let's go to the periodic table and see. Looking at the periodic table and also reminding myself the periodic table we deal with has a little key here. Notice what we have. We have the atomic mass on top and we have the atomic number on the bottom. So it tells us the proton number and electrons if it's an atom. It tells me the mass number. For right now, we're going to round off this mass to 12. Okay, now let's go back to the element that we're talking about. Hydrogen. Here it is in all of its glory. And let's make it bigger. And we can see information about hydrogen. We can see that it has a mass number rounded to 1. And it has, more importantly, a atomic number of 1. Now, if you notice in the example I gave you hydrogen 1, hydrogen 2, and hydrogen 3. Those numbers I'm giving you are the different types of the same isotope, of the same element. Now, what they're leaving out is this number 1. And the reason they're leaving it out is because you don't have to have it. By having the element H here, party people, it is implied you have 1 proton. Now you may say to me, Mr. Grodsky, why is it that if it is 1.00794, why don't I see a 2 or a 3? Well, we're going to find out today that this mass number is an average of all of these together, but using their relative abundances in nature. Meaning when I average all of these 3 different forms of the same isotope, I get this number because most of all of hydrogen exists as hydrogen 1. Now, while I'm here talking about it, what does this mean to be hydrogen 1? In this example, it has a mass of 1 and it has 1 proton. We know a proton has a mass of 1 atomic mass unit. So to get neutrons, as we have already learned, we subtract. So this 1 minus 1 has 0 neutrons. 2 minus 1 has 1 neutron, and 3 minus 1 has 2 neutrons. So what I'm saying to you, party people, is that these 3 elements of the same element are differed just by how many neutrons are in their element. It doesn't change their charge because neutrons, as we see in table O, has a 0 charge. That's why they call it neutral. Okay? So my friends in chemistry, all we're changing, okay, is the mass of the atom. So the atoms has a more predominant or bigger or thicker nucleus. In the case of hydrogen, you just have 1 proton. Hydrogen 1 has just 1 proton in its nucleus. Hydrogen 2 has still 1 proton because the atomic number is still 1, but it has 1 more neutron in its nucleus. Looks something like that. Hydrogen 3 has 1 proton because that's what makes it hydrogen, but it has 2 neutrons. So its nucleus is more massive. In fact, if you look at this carefully, you'll see that the hydrogen 1 compared to hydrogen 3 compared to hydrogen 1 is 3 times as massive. It has a nucleus of mass of a 3. Rutherford's experiment states that the entire mass of the atoms in the nucleus. Well, this nucleus is 3 times more massive than this one. And that changes its properties somewhat. In fact, hydrogen 3 is radioactive. So when you say I have hydrogen, you have to associate it with what its mass number is to tell me which form of hydrogen I have. We don't normally deal with these numbers in the bottom because by saying H you have 1. Let's go back to the mass spectrometer. Now, we discovered that hydrogen had different forms of the same element by having different number of neutrons by the mass spectrometer. Very simply, we take the sample of hydrogen we get from nature, which is going to be a mixture of all these different types of hydrogen with different number of neutrons. In this example, we vaporize the sample if it's not already vaporized. We hit it with an electron beam. Basically, we're adding, in this case, electrons. So we're adding electrons to the hydrogen to make it charged. So all of these hydrogens are now going to become ions. They're all negatively charged because they're holding on to an extra electron. Then we're going to basically shoot them through a magnetic field. Now, of course, what we're going to do at the end here is probably make this a positive charged, and what's going to happen is these negatively charged ions, some of them heavier than others, are going to race toward this positive. Now, before they do that, we're going to throw them through a magnetic field. You can think of the field as a sort of wind that's pushing on them. So this field is attracting them with a force pushing them this way. So as I said in class, think of this as a big heavy car trying to make a turn. And we have this force of the magnetic beam bending it. But think of this, the heavier car, or the heavier what? Isotope with more neutrons, in this case H3, has what? 2 neutrons with its 1 proton. As a reminder, this is 1 neutron with the 1 proton, and this is 0 neutrons with the 1 proton. The heavier one, that's 3 times more heavier, okay, can't make that turn, so it goes farther down the detector plate. Whereas the lighter one, being 3 times as what? Light, okay, can make this turn easier, and it hits the detector plate way over here. And what we do is we measure the distances between them. In fact, hydrogen 2 hits the detector plate right in the middle. And we measure the relative distance that they hit this plate, and that's how we come up with H3. We found out that H3 goes what? 3 times as far than H1, and it matched our understanding that this has 3 times the mass than this has. So we found that all elements have isotopes by the mass spectrometer, okay, which is another way to figure out the mass of elements. Before, we were taking boxes of gases at STP and figuring out their mass. Now we can use this and using the distance. Now, if we were to charge this with carbon 12, okay, notice I'm giving you the 12. The carbon 12 is much heavier than this. In fact, 12, you notice, is 4 times bigger than 3, right? 4 times 3 is equal to 12. So 12 is 4 times bigger than 3. Carbon 12 would hit this detector plate 12 times farther than H1, or 4 times farther than H3. We can measure that distance. That's how we come up with it. Any case, let's get back to what we're dealing with here. So let's give in 3 forms of carbon here, and let's figure out protons, neutrons, and electrons as a review. All right, well, these are isotopes. How do I know? Same element, same symbol represents the same element, different mass number. That's an isotope. Okay, now, if you go to the reference table, you'll see that carbon is atomic number 6. I don't have to write it because the C is there, but I'll put it in. These all have 6 protons, or a 6 atomic number. It's the number that identifies the element. Now, so protons are all 6. Why? Because they're all carbon. If you don't know where to find this, let's look at a periodic table. Going back to our periodic table that we were just annotating before, here's our carbon. And right here, I'm going to find it where it exists. And I see the atomic number, okay, is 6. It has 6 protons. Now, We can round that to 12, and there's a reason why it's closer to 12. We'll get to that, but there's 6 protons. Now, if it's an atom, it also has 6 electrons. You say atom, I say neutral. Atom. Well, okay. Well, the point being is that carbon atoms, the electrons have to equal the protons. Back to our page. Now, isotopes are just different forms of the same element. Element implies atom. And atoms always imply neutral. So we didn't say ions. We're saying elements. And elements are written as atoms. So, my friends in chemistry, these are all 6 electrons. The proton number equals the electron number if you say the word atom. Neutral. Okay, now the neutrons. Well, we learned that a proton has a mass of 1, right? And a charge of 1. A neutron has no charge but a mass of 1. This is from Table O. Table O tells us this. So all the mass of the atom comes from the nucleus, which has protons and neutrons. The electron, if you remember, had a 0 charge and a 0 mass and a negative 1. In fact, its mass is 2,000 times smaller, but it's insignificant. So how do we get neutrons? We subtract because the top number is protons and neutrons. Bottom number is neutrons. So 12 minus 6, 6 neutrons. These are electrons, these are protons. 13 minus 6, do my math, it's 7 neutrons. Then 14 minus 6, 8 neutrons. Hope you can see that the difference between carbon 12, carbon 13, and carbon 14 is just the number of neutrons in the nucleus. It doesn't change the charge because neutrons have no charge. All right, very important. Now let's go on to the first types of questions. Now, we're going to work ourselves into something called the weighted mass problem. Now, this is very vital. Now, in order to understand this problem, what we're going to do is figure out our grades. Okay, let's pretend I have the following grades. Now, these grades were how I used to run a course. Okay, it's not how our current course is run, but very similar. So let's do this. A tall chemist uses the following category to determine the quarter grade for his class. 60% of all test grades. So I've got test here. And the test grade is 60%. Okay, then I have lab grades. And the lab grades are 10% of the overall quarter grade. And then I have quiz grades. And then quizzes are 10%, my bad. And labs are 30%. I can make that change. Okay, so that's the breakdown of how you get your grade. So what we're saying is your entire quarter grade is due to 60% of your tests, 30% of your labs, 10% of your quizzes. That's how the grade's made out to if you did in categories with those percentages. Now, let's pretend you have a test average of 70, all right? And you have a lab average of 80 and a quiz average of 90. Well, if you were to put this in your calculator, 70 plus 80 and divide by 3, you would actually get 80. Right? Because 80 is the middle number. So if you were to do a straight average, now in math, a straight average means you take all the numbers, add them up, and divide by how many numbers you have. But when you do a straight average, you're assuming that each one of these has equal weight. So if I have 3 numbers, that means each one is 33.3% in weight. But no, you can't do that here. So what you do is you have to consider the weight or the percentage of each. So to do this, what we do is we take 60% of 70. So I take my 70 and I'm going to times it by 0.6. Okay? Now you say, why am I doing that? I'm finding 60% of 70. So if my dress that I want to buy is 60% off, remember you move the decimal place 2 places to the left and you times by that number. So you get 70 times 0.6. And I get 42. Now what does this mean? This 42 means 42 of my first quarter points came from that. All right, we'll get back to that. Now 30% of 80. So I take my 80, I times it by 0.3. My dress is 30% off, so how much am I going to save? So I take my 80 times 0.3 and I get 24. Let's go back to magenta and we go 24. And let's do the same thing over here. Let's find 10% of 90. That one we can do in our head, but let's make sure we get it right. 90 times 0.1. Moving the decimal place 2 places, and that's going to give me, going to magenta, 9. And what do I do with these numbers? I add them together. So I take my 42, my 24, and my 9, and I add them together in my calculator. And that's how you do a weighted average, where you consider the different percentages of each. 42 plus 24 plus 9 gives me 75. And that is my average. Wow, kind of weird. My average is 75, yet I have so many good grades above that. Well, why? Look at this for a second, guys. 40% of your average, or 40% of your weight, is where your good grades are. You have good grades in places that have the lowest weight or the lowest meaning. Your lowest grade is with the test. So it brings all of these down closer to 75. Look at this for a second. This is really important. You would expect to be 80 if you do a straight average. But my friends, in chemistry, you're at 75 because most of the weight, right? The weight is the percentage, is at the test. So your lowest grade is with the highest weight. So it drove your what? Average down this way. These guys over here had less weights. So even though your better grades are on this side, they couldn't overcome the bad grade in this highly weighted value, part of your quarter grade. Now that's how it works when we average isotopes. Now this isn't your problem, but pay attention. Carbon 12 and carbon 14 are the most common isotopes of carbon. Let's pretend we do a straight average. Let's gonna average these isotopes. Now, if you do that, you're saying that 50% of all the carbon is carbon 12 and 50% of all the carbon is carbon 14. If I do a straight average, I will get carbon 13. And that would be what is written on the periodic table. Let's go to the periodic table. Well, carbon 13 is not written that way. It's carbon 12.001. Wait a minute, what's happening here? Why am I closer to 12 than I am 13? Well, getting rid of this, okay, the number actually is not 13. The number is actually 12.01. Why am I so close to the 12? Well, it's because these percentages are not 50%, party people. These percentages are actually like this. There's actually 99.9% of all carbon, right? Has a greater what? Has a greater weight. And of course, carbon 14 is 0.01%. So because most of all the carbon is carbon 12, doesn't it make sense your carbon's going to have a weight that's closer to 12 than it would be to 14? And the answer is yes. Remember, our test grade, which had the highest weight, it made sense that your overall average was closer to the test grade than the others because it had the greatest weight. So this is how we do things, guys. We look at the relative abundances in nature. We look at these percentages, and that's how we figure out the isotopic mass, the average. Now watch how I do number 3. I'm going to model number 3, and then I'm going to ask you number 4 with my answer. So here comes number 3, and this is very important. You must be able to do this. Naturally occurring sulfur consists in 3 isotopes. So let's just write them. Okay, we have sulfur 32, we have sulfur 33, and sulfur 34. All right, sulfur 32 has an abundance of what? 95.02%. What does that mean? That most of all the isotopes of sulfur exist as sulfur 32. Sulfur 33 has an abundance of 0.79%. And sulfur 34 has an abundance of 4.19%. My friends, clearly my number is going to be closer to S32. But let's go through the math, okay? I'm going to white out some things below to make this clearer, hopefully. All right, give myself some space. All right, so let's do this. Now, how do we do this? How do we do a weighted average? Very simple, okay? What you're going to do is take 95.02% of 32. So I take 32. Now, when we make a percentage, we move our decimal place 2 places. This is 0.9502. And I'm going to come up with a number. Put that in your calculator. Let's find 95.02% of 32. So 32 times 0.9502. And that gives me 30.4, let's make that 1, okay? Now, going back here, we're going to find 0.79% of 33. So put 33 times, now we do percentage, you move the decimal place 2 places, so this is going to be 0.0079. Let's go find that number. So we have 0.79% of 33, so we take 33 times 0.0079. And that gives me a very small number, because it's a small percentage, 0.2607. And I guess I wanted to do that in blue to keep myself color coordinated. All right, and I guess that's not really working. So let's just keep it 0.2607. And then we're going to take 4.19% of 34. So we take 34 times, moving the decimal place 2 places, right? 0.0419er. Let's go find that number. Let's make it in blue. 34 times 0.0419. And what I get is 1.4 to make that 5. And what I do is I add these numbers together. That's it. And I find my number. Let's add them together to see what we have here. So we have 30.4 plus 0.2607 plus 1.425. And what I get is I get 32.08, and let's keep this to, well, it's a percentage. Let's just go, well, it's 5.7. So we can round that to 32.09. I'm just going to do that to 4. And that is what sulfur's mass is. Lo and behold, party people, you've got a decimal place. Why do we have decimal places on the periodic table, my friends? Why? Why do we have decimal places? Because we're averaging all of the isotopes that exist. But my friends, in chemistry, let's look at sulfur. It's 32.06. What does that mean? It's closest to 32. What does that mean? That means that the most abundant and most popular isotope is sulfur 32, right? If the number is closest, right, the 75 was closest to 70, in this case, the average is closest to 32, this is the isotope that occurs in nature the most predominantly. So if I go back to my reference table and look at some other questions, what do you think is the most predominant isotope of fluorine? It's 8.998, which is closest to what? Yeah, the most abundant isotope of fluorine is fluorine 19. Now the fact that it's less than 19 means the other isotopes must be lower. That's how it works. Okay, so this is called the weighted mass problem, and what you're doing is you're finding this decimal place, and the decimal places we get in the periodic table, my friends, are nothing more than the averages of the isotopes that exist using their relative abundances in nature. Please try number 3, and I'm going to get back to pause my video now, try number 3, and then I'll show what I have. Okay, so welcome back, and you can clearly see that my answer is 86.41, and that's how I'd write it. That's my weighted isotopic mass, my average isotopic mass happening here. It's got a decimal place because I'm averaging all of the existing isotopes that differ by the number of neutrons, proton number staying the same, that's why it's still strontium, and considering their abundances in nature, okay, that's given to the problem, I find the exact weighted average. And all I did was I found the percentage of each of these atomic masses, and then I added them collectively together. Notice my number, okay, is much bigger than the 86 and 84 because these have the lowest mass. My number is more indicative of the higher numbers because these are existing in larger amounts. So that's how you do it. I'd like you to continue on with the rest of this worksheet, okay? And I would like you to do your best and see how you do with that. And of course, look with the key to see how well. All right? So enjoy the rest.